Hello, it's Vagt-Bendoski here. I'm gonna do a little walkthrough of the code for my final project in data privacy. This project implements differential privacy over a neural network, and let's get into how that works. First, we've got all of the imports. Um, is regular, y'all know this, and we're using this same random seed to make sure I get consistent results across however many times I run it. And we're using the planar data set from the data utils package just as something to look at while we do this, as an experiment, if you will. And here we've got the Gaussian mechanism defined, and the first part of this neural network that we're building is going to be initializing the parameters, and the way we're going to do that is randomly. And this is important because if you don't do them randomly, then sometimes it can end up symmetrical and really reduce the computational power of your neural network. So we've got them all initialized randomly there and then put into this little dictionary. And then we've got the forward prop. This is how we make predictions and how we push data through the neural net. And the way this works is we've got all of the matrix math or vectorized math to make sure that all of the numbers go in the right place, and when they're ready to be calculated, we use the sigmoid activation function. And this activation function is good because it's got like a good scaling. Yeah. And then this part will compute the cost of the neural net. And the next part that we have to be able to update the cost and everything is our backward propagation, which will push all of the results of the prediction back through the neural network so that we know where exactly we need to update things to make the neural net better for each training iteration, each epoch. And now we've got the secret sauce, the update parameters function. This will take our gradients, which will be calculated by the compute cost and the backpropagation function, and we're going to update our weights according to those gradients and the learning rate. And if use differential privacy is set to true, we will also be adding noise via the Gaussian mechanism to these gradients. And the default values for that is going to be a sensitivity of 1, an epsilon of 1, and delta of 1e to the minus 5. But if you don't turn on use differential privacy, it'll just be a regular neural network gradient descent. And then this model function here will just initialize the model and call all of the updates. And then we can predict data using this prediction function. And that's the model. That's how everything is set up. Now I'm going to talk about the results. Here we've got a model with no differential privacy, just as a baseline, with 4 hidden layers and 1500 epochs. It's able to classify this data looking like this. It's very nicely not overfit. It's a very good classifier. This is kind of what you want to see on a data set like this. And once we introduce differential privacy, just using those previously discussed default values, we get a graph that looks like this, and that blows. That's a terrible classifier right there. This makes sense because we're adding a lot of noise to the gradients, so it doesn't really know which way to go. But if we try and increase the capacity with 15 hidden layers and 2500 epochs, we get something like this, which also blows, honestly. And what we need to do in order to get a good classifier is actually up the epsilon. So we're adding less noise and we're protecting less privacy. And then we get a classifier that looks like this. And that's pretty good, honestly. It's pretty close to the first one. It misclassifies a few of these things along the edge here. But this is good. And really, this brings us back to the eternal struggle of this whole field, which is that the more privacy we add, the less utility we have, right? So as we decrease epsilon, or we leave it at 1, we're going to have a worse model. It's going to be less useful. But if we don't care about privacy at all, we could even go up to this first one and have a great classifier. And that's sort of data privacy in a nutshell, isn't it?